All right, let's do it to it. So like I said, this is the last new material before your 1.4 to 1.6 quiz. Everything we're doing today is purely Algebra 2 knowledge, but I am going to just ask you to understand that algebra knowledge at a slightly deeper level than before. And I mean, that's essentially what Precalculus is anyway, right? It's just Algebra 2 at a slightly deeper level. Not a whole lot of brand new mathematics. What we're talking about today is in behavior. And rather than reading all of this, what I'm going to do is I'm going to tell you. You could tell the in behavior of a graph, meaning which way, well, the in behavior of a polynomial, which way its two endings point based on two pieces of knowledge. And both those pieces of knowledge are going to come from your leading term of your polynomial. So who knows what all is after that? But this, called by itself, is called a power function. This power function alone dictates the behavior of the graph. Now, it doesn't predict the spaghetti wiggles in between the endings, but it will describe the two endings to us. We need to know two things. We need to know, is that leading coefficient positive or negative? So A sub n. Is A sub n positive or negative? And the only other knowledge we need is the degree of the polynomial. Is degree n even or odd? That is enough information for you to determine what the endings of a polynomial look like. Called in behavior. Very simple. Okay. There are four pictures here. Reason why is these two, the endings point different directions. These two, the endings point the same direction. As it turns out, if your endings point different directions, this is an odd degree polynomial. That means if the degree is even, the endings must point the same direction, and that's what we have going on down here. Okay. And it'll be back on the screen in a minute, don't stress. Let's focus on these two up here for now. If you were to try to connect the arrows that you see here with the straight line, there, I connected the two arrows. The slope of this line, not this pencil, the slope would be considered the average rate of change. My question is this average rate of change positive or negative that I currently have on here? Lots of people can shout it out. This is a positive average rate of change. Reason why? Is because the leading coefficient is positive. And by the same logic, if you connect the arrows with a straight line, with a straight line, there we go, the average rate of change would be negative. So the leading coefficient of this odd degree polynomial is negative. Nothing new here. We've already discussed that this year, actually. The one shred of new knowledge of today is going to be how we describe our in behavior with symbols. In Algebra 2, you used symbols like this. You don't have to write this. Let's say this goes right and down. Bless you. In Algebra 2, you would have written as x goes to positive infinity, y goes to negative infinity. As I go right, I go down. That's what that says. We have a better way of writing that. It's more specific and it's more compact, and well, it doesn't use words. We call it limit notation, and it's very, very tiny on this paper. So what I'm going to do is I'm going to write it larger. I'm going to write exactly what it says, just bigger, so I can describe what's going on there. This one right here that is so hard to read says limit, and underneath limit, or lim, is x arrow infinity, and then you have an f of x equals. Here's how we read that. The limit as x approaches infinity of f of x is. And limit can be thought of being the goal of the y values, because f of x represents the y values. So it says, hey, what are the y values heading towards when x is heading towards that? That's what that says. And the answer to that is infinity, because they're pointing up. And it's important that you are comfortable with limit notation, because the entire first chapter of AP Calculus or college level calculus is limits. That's what the chapter is called, limits. Yes? No, it's exactly the same. It's just it'll be a limit instead of this. Because I didn't use limit notation in Algebra 2, did I? Did I? Towards the end of the year maybe? Not at the beginning? What's that? Oh, as a side. But I didn't test on it though, did I? I didn't think so. Okay. Yeah. But yeah, it's the exact same symbols. And we can do it over here. This time I'm going left and down. So the limit as x approaches negative infinity of my y values is, and we said it's headed down, negative infinity. So since we now know what those little limit things say, and going left is always towards negative infinity, going right is always towards positive infinity, I'm just going to write on the pictures now. This one says, the limit as x approaches negative infinity of f of x is. Meaning, as I go to the left, my y values, well, looks to me like there's an up arrow. The limit as x approaches positive infinity of f of x is. It literally says, what are these y values doing as I head to the right? Looks to me like they're shooting down. Negative infinity. Man, who put that freaking picture right there over where I have to write? Negative infinity. So before I go to the even degree polynomials, would you like to ask me any questions about leading coefficients, degree of the polynomial, in behavior, limit notation, any of that?
So what is the degree of the polynomial back to the graph?
So the degree of the polynomial determines if the endings point the same direction or opposite directions. That's all it does. So these point opposite directions because the degree was odd. These point the same direction because the degree is even. The trick for these is positive people smile, negative people frown. Both endings point up for even degree polynomials if the leading coefficient is positive. Both endings point down for an even degree polynomial if the leading coefficient is negative. And then we just need to figure out, what am I trying to say? Fill out, there we go. We just need to fill out our limit notations that describes our end behaviors. I used purple, I used red. The limit as x approaches negative infinity of f of x is, this says, as my x's go to really far left, my y values go to, looks to me like it's up. And you know what? They point the same direction. So as they go to the right, they're also going up. And then over here, as you go far left, your y values looks to me like they're headed down. Actually, both headed down. Negative infinity for both of these graphs. That's the behavior. So other than the symbols, shouldn't be new knowledge. Maybe it's dusty knowledge, but it shouldn't be new. Are we calm, cool, and collected enough for me to turn the page? No questions. All right. So we just did a bunch of stuff with like images, right? Here's the exact same crap, only in words. We have 2 lines because there's 2 kinds of things to talk about. It says, consider domain and range for each degree family, meaning even and odd. So as x goes to the right or x goes to the left, what do we notice about the y values? So let's do the odd ones first because that was on top. So for odd, what do the endings do? Our options are same direction or opposite directions? Opposite directions. Endings go opposite directions. For even degree polynomials, endings go the same direction. What happens to the graph if you change the a value from positive to negative? And this is true for any function. It'll change the direction of the arrows. So of every arrow, right? So in normal old words, turns it upside down. But yeah, the net result is that every arrow will point the opposite direction. So we say, I don't know, how do we want to word that? If sine of A, let's do it in quotes like they did, changes, all endings go the opposite direction. That feels good. So everything that was pointing up will now point down. Everything that was pointing down will now point up. Boom, there it is. So that was just the picture stuff in words. Okay. These next 2 say to use a graphing calculator. So I have my graphing calculator handy. It's right here. But I'm going to answer the first 4 questions before sketching the graph, before even touching a calculator, okay? First of all, the degree of this polynomial. I just need you all to shout it out. What is the degree of this polynomial? 3. Those of you that shouted out, thank you. That's an odd number. The leading coefficient, I just need you to shout it out. Positive or negative? Negative, good. Okay, here's what we know then. I mean, we don't know about the spaghetti noodle in between the endings, but because it is an odd degree polynomial, I know the endings point different directions. And because the front number is negative, I know I have a negative average rate of change between the 2 endings. That's going to allow me to fill out my limit in behavior. The limit as x goes to negative infinity of f of x is this side. It's pointing up. And the limit as x goes to positive infinity of f of x is this side. It's going to the right. It's pointing down. Before I touch my graphing calculator, see if anybody can remember from yesterday when we talked about it, or the day before. I can't remember now. If it is a 3rd degree polynomial, what is the maximum number of turning points it could have? Chris? 2. N minus 1. What's the maximum number of inflection points it could have? 1. N minus 2, which I believe is outside the scope of what AP is going to require you to know, just so you know. This thing could have 2 turning points. Let's find out. Handy dandy calculator. Negative x to the 3rd plus 2x squared plus x plus 1. I'm hoping that the standard zoom is good, so zoom 6, because that's zoom standard. No, there it is. It does have 2 turning points, but it only has 1 real 0. Well, if you recall, from the last lesson, I don't remember if it was yesterday, but from 1.5, we said odd degree polynomials must have at least 1 real 0 because the endings point different directions. There you go. This one only has 1. So since it has 1 real 0, how many complex zeros does it have? 2. Has to. Fundamental theorem of algebra says degree in polynomials have in zeros. Complex zeros. So it has 2 complex and 1 real. Technically, that's 3 complex zeros, but 2 of them are non-real complex. 1 of them is a real complex. Anyway, it does have 2 turning points, and this picture looked something like this. Good enough. Good enough. Last period, one of the students said, so are turning points just the extrema? And I said, well, all turning points are extrema. All turning points are either a maximum or a minimum. However, there are some extrema that are not turning points, namely endpoints. So if you have a graph that comes to an end somewhere, an endpoint is an extreme value. It's either a maximum or a minimum, but it's never a turning point. However, all turning points are maximums or minimums, always. Cool? Yes? Okay. Let us do it again. This time, you guys can shout it out. What's the degree of this polynomial? 4. Is that even or odd? Even. Great. My leading coefficient. Is it positive or negative? Positive. It's just a 1. It's not written, but it's definitely there. So even degree polynomials, the endings point the same direction. And positive people smile. I don't know about the spaghetti noodles, but I do know that the 2 endings go up because it is a positive leading coefficient. That means my y values on either the left or the right side are both going to be heading to the same place, positive infinity. Now this is a 4th degree polynomial, so shout it out. How many turning points could it have? 3. Up to 3. Are we guaranteed 3? Of course not. We could have up to 3. We are guaranteed at least 1 turning point though, because the endings point the same direction. There's no way that it goes left up, right up without turning somewhere in between. So we're guaranteed to have at least 1 turning point. We could have up to 3. Let's find out. Hoping that the standard zoom is still good. It was. The standard zoom still works. And we're just sketching this thing. But look at the picture. How many turning points does it have? It does have 3 turning points. It looks something like this. Ta-da. Oops. Picture not drawn to scale. Looks something like that. So that leads us to something that we had already realized as a class a few days ago. The graph of the graph of f has at most n minus 1 turning points. These are points at which the graph changes from increasing to decreasing or vice versa. And a graph has at most n, meaning the degree, real zeros. But you could have some complex zeros. So since we're talking about the number of zeros that are possible, I'm going to ask the class a question, and I'm going to ask all of you to give me a number answer. I'm going to ask all of you to talk. Actually, is this a yes, no? How about this? We'll start with this. We're going to go with a yes or a no. Your answer is either going to be yes or no. Everybody's going to choose one, okay? Class, is it possible for a cubic, a degree 3 polynomial, to have only 2 real solutions? Yes or no? Yes. Heard a mixed bag. Most people said yes. Now, a couple people said no. And let me tell you why they said no. They heard me say only 2 real solutions. They made an assumption. They assumed I meant only 2 real solutions with no multiplicities. And what they were thinking was, it's impossible to have a degree 3 polynomial that has 2 real solutions and 1 complex solution. That's impossible. But yes, it is completely possible to have 2 real solutions. Let me draw an example of a cubic that has 2 real solutions. This one just happens to be a repeated solution, but it only has 2 real. So cubics can have 1 real, 2 reals, or obviously 3, you know, if I did this. Whee! Okay, that one's got 3, okay? So, yes, all of those are possible. So, let's ask the question a little bit different, and again, I'm asking my class to give me a yes or a no. Class, is it possible for a cubic, a degree 3 polynomial, to have an odd number of complex zeros? No. I should have said non-real complex zeros, but no. And the reason why is because non-real complex zeros must come in conjugate pairs. They always happen in pairs. Yes?
What's a complex zero again?
A complex zero is a solution that involves an imaginary number. Okay. Yes? Yeah, complex conjugates look like this.
Oh, yeah.
Yep. Yeah, they're called conjugate pairs. So they always happen at the same time. And they always are going to be the reason why they come in pairs, if you want to think of it, is because they're the result of a quadratic that simply doesn't hit the x-axis. And since all quadratics have 2 solutions, these things are going to come in pairs, always. Good? All right. If the polynomial function has a factor that is repeated, these duplicate roots are labeled as, we say they have multiplicity of 2 or 3. So let's just say as a multiplicity greater than 1. They're repeated roots. So they could happen 2 times, 3 times, 4 times, 5 times, 17 times, whatever. If the function f has a real zero, c, that has an odd multiplicity, so I've got a factor that's got a power of 1, of 3, of 5, of 7 on it, then how does the graph behave at that number? It crosses through the x-axis. At that number. But it could do that cross in 2 different ways. One of those ways is, this is my x-axis. One of those ways is going through it in what could be considered a straight way. Like if you zoomed in real close, it would just look like a straight line went through the x-axis. Another way is going through with some style. Going through with a wiggle. And this happens at an odd multiplicity of 3, 5, 7, any odd multiplicity of 3 or bigger. And what's significant about these is anytime you go through the x-axis with an odd multiplicity of 3 or bigger, and this is review because it was in our lesson 1.4 notes, guarantee that that is an inflection point every single time. Because if you notice the picture I drew here, to the left is concave up, to the right is concave down. That's what happens when you go through with some flair. Now, if our function f has a real 0 c with an even multiplicity, so our factor has a degree 2, 4, 6, 8 on it, then the graph of f will, and the official verbiage is touch the x-axis. And we hopefully you all know that this means bounce off. Because in Algebra 2 we say bounce. But AP might say touch instead of bounce. And that's happening at x equals c. And obviously you're either going to be above the x-axis or below the x-axis when that happens. Now I told you every time you go through with an odd multiplicity of 3 or bigger, it's guaranteed to be an inflection point. Every time your graph bounces off the x-axis, you're guaranteed that that's a turning point. It has to be. Because it stopped increasing and started decreasing, or vice versa. So these always produce inflection points. These always produce turning points. Always. Cool? Need a mosquito? The direction said use a calculator to sketch it, but then here's a picture of that sketch, so we don't even need to grab our calculator. Okay, there it is. It's just there. Ta-da. This is the polynomial in factored form. It has 2 real zeros because there are 2 different numbers that make the inside equal 0. It says in the graph at the right, label the zeros and describe the behavior of the roots. That means, the factor. It's the behavior of the roots. This is the same thing as saying factor. The behavior of the factors. Anyway, we've got one right here at x equals -2. At x equals -2, am I bouncing or am I crossing? Crossing. Why did that happen? Because that factor had odd multiplicity. And it did it with some flair. Looks like a cubic. At x equals 1, bounce or cross? Oh, I touch or cross, I should say. It touches the x-axis. So we'll say we touch at x equals 1 because the factor x minus 1 has an even multiplicity. So questions that weren't asked, but you still need to be comfortable with. First, class, say a number. What is the degree of this polynomial? This is the answer 3 times, and this is an answer 2 times. So that's a total of 5 answers. So this is the degree 5 polynomial. 1, 2, 3, 4, 5. Because this one happens 3 times, this one happens twice. So this is a degree 5 polynomial. It could have had up to how many turning points? 4. Class, lots of voices. How many turning points does this graph have? So some people say 3 and some people say 2. There are only 2 turning points. This is not a turning point. This is an inflection point. Inflection points cannot be turning points. It's not possible. Inflection points are places where your concavity changes, but the behavior of the average rate of change does not shift. This is a positive average rate of change, a positive average rate of change. But I changed from concave down to concave up. So this is an inflection point. This is a turning point, and this is a turning point only. There was a hand up and now it's gone. Was it you, Sage? What's up?
Well, you said that there's 5 answers and there's 5 exponents, but I was just like...
There's 5 solutions. They're not all distinct, meaning different, but there are 5 solutions.
What exactly do you mean? Because I thought a solution was where it was like intersecting the x-axis.
Yeah, yeah. It hits this x value 3 times, and it hits this x value twice.
But what is that? What do you mean by that? How do you hit an x value 3 times?
Well, that's what the multiplicity implies.
Does it like show it? Or
Yeah, see how it looks like a cubic?
Yeah.
There you go. That's you showing that it has that answer 3 times. And this looks like a parabola, right? It's you showing that that answer happens twice. So it's a degree 5 polynomial. It could have had 4 turning points and only has 2. Here's the one that really stumped last period. Looking at this graph, class, how many inflection points does it have? I heard 1, I heard 3, I heard 4. So only 3 people spoke. Sounds like a mixed bag, huh? Tell you what, I'll circle the inflection points. This is guaranteed to be an inflection point. This is concave down, right? But this is concave up, right? Right there? That means there's an inflection point somewhere but here-ish. And see how this looks like a bell, but this looks like a bull? There must be another one somewhere around here as well. So it has 3 inflection points. Two turning points, 3 inflection points. Neat. Yeah.
Will it always equal the degree?
No, it's a coincidence that they add up to 3. Or add up to 5, excuse me. And I can prove it. What's the degree of that? No, I mean, well, what does it assume? You can safely assume it is 2. How many turning points does this parabola have? 1. How many inflection points does it have? None. So they don't always add up to the degree. Sometimes they do, though. That's a good question. Nope, it was coincidental. I was actually a little worried until I thought of the parabola example because I'd already said no. I was like, maybe? No, okay, no. All right, intermediate value theorem sounds really, really fancy, but it's actually a very easy thing to understand. It literally says, if your y values changed from positive to negative when you moved from one x to the next, you must have passed through the x-axis. That's literally what it says. If you can find 2 y values where the signs change, meaning you went from positive to negative or negative to positive, then a 0 of the function will fall between those 2 x values. I mean, how did you go between positive and negative y's unless you passed through y equals 0, right? It's called the intermediate value theorem. It says use the intermediate value theorem to explain why this function must have an x-intercept on this closed interval. That means between these 2 x's. It's a very simple thing to do. Let's figure out what our y values are. You're plugging in a 1 here, you get 1 plus 3 minus 6. That is negative 2. Then you substitute in x equals 2. You get 4 plus 6 minus 6, which is 4. You see how we went from negative y values to positive y values? Because the sign on our y values changed, we went from under the x-axis to above the x-axis. We must have clearly hit the x-axis somewhere between x equals 1 and 2. So you could say since sign of y values changed, g of x must have an x-intercept on 1 to 2. So there's an x-intercept somewhere between those 2 x values. It's guaranteed. Sounds fancy, doesn't it? It's pretty freaking easy, though. You can use the intermediate value theorem to prove really neat stuff. Like there is a cubic that's exactly 1 less than its cube root and things like that. Like you use the intermediate value theorem to prove it's true. Yes?
For answering this question, did you have to say x-intercept, or could you say it passes?
Well, it just says must have a root or x-intercept.
Oh,
So I'm just using their words. It could have said solution, and I would have said there must be a solution between. But yeah. Or you could just say, explain why there has to be a solution. You go, well, clearly I passed through the x-axis. Just things like that. You just had to make it obvious to the graders for the AP exam that you knew what you were talking about. And there was another hand up and then it went down. You changed your mind? Okay. Putting it all together. It says list each real zero and its multiplicity. I see two different numbers that will make the inside equal 0. What's the 0 here? What does x have to equal? -2. What is the multiplicity of this? It is 1. Yeah.
So the second one, to the third power, that's going to be like a elliptic and cubic.
Yes, and I'm actually going to sketch it for us. But yes, it'll have a cubic look at that 0. So what's the 0 for this set of parentheses? 3. X equals 3. And Max already said it, but it's got a multiplicity of 3 as well. Let's do this part, and then I'll sketch this for us. Because I have multiplicity 1 here, does it cross the x-axis or touch the x-axis at x equals -2? Cross. And it'll cross like a line because it's multiplicity 1. Because this is multiplicity 3, does it cross or touch? It's going to cross, and it's going to cross like a cubic. All right. So what is the degree of this polynomial? This is a degree 4 polynomial with a positive leading coefficient.
So because if there's 2x to the power of 1, that only counts as 1 extra, like additionally to the 3. If you're looking at the exponents and there's the third degree one, there's the cubic one, and then there's x to the power of 1 twice.
No, it's this one and this one adds up to 4.
Oh, okay. That's not how I was looking at it. I got it.
Yeah, this answer happens once, this answer happens 3 times, so that's 4 answers, degree 4. The front number is positive, and that tells me that my 2 endings both point up. I know that I'm going to cross with some flair at x equals 3, and I'm going to cross like a straight line at x equals -2. Let's get a quick little sketch going. They're both up, and I said I'm going to cross with flair at 3. So it's going to look something like this. Cross with flair, but go up. There, I crossed with flair. But I'm going to cross through this one without flair. So there we go. There's a good look. What is the maximum number of turning points this degree 4 polynomial could have had? It could have had up to 3. But knowing that the graph looks like this, how many turning points does it have? Only 1, right here. It has 1 turning point. It could have had 3. It has 1. Now, the next one talks about concavity, so let's do it like this. Looking at the picture, I'm looking for you all to say a number. How many points of inflection does this graph have? Such a mixed bag of answers. Okay, guaranteed this is an inflection point. And there's only one more. Somewhere here-ish. All that's concave up. All that's concave up. That's concave down. And so let's estimate them. I don't know. You want to say that's at x equals 1? Okay, so let's just say this was at x equals 1. We are concave up. Everywhere from -infinity to x equals 1. And then once again after 3. And we just estimated without grabbing a graphing calculator. That's what the graph kind of looks like. So it's concave down between 1 and 3. Never put brackets on concavity. And this last question down below, it really just wants us to say all the things that we know are true about this. So in behavior, they both point up. So the limit as x approaches negative infinity of f of x is positive infinity. And the limit as x approaches positive infinity of f of x is, also positive infinity. All polynomials have the same domain. All real numbers. The endings point the same direction, guaranteeing us a global maximum or global minimum. This one has a global minimum. Where would you like to say that that y value is? Negative 15? Negative 4? It looks more like negative 14, but sure. Let's go with negative 14. Goes up for all infinity. What's next? How many turning points do we see? Yep. One here, one here, one here. The endings point the same direction, and there are 3 turning points. My zeros, what's their multiplicities? 1, because they go through straight multiplicity of 1. So based on all the things I just said, what is more than likely the degree of this polynomial? 4. There you go. That's pretty much all you can, I mean, you can tell me how many inflection points it has if you'd like to. How many inflection points do you see? 2. We're getting there. 2 inflection points, probably here and here. Yeah. Yeah, you know, you're all going to be strong nerds before I'm done with you.